it pops to the next slide. Okay, last time we did section 3.2, which was starting the discussion about showing relationship or association between two quantitative variables. And so today's the second day of that, section 3.3, which does linear regression. So we're going to not only look at scatter plots like this, but think about fitting a line to that data, coming up with the equation of that line. So we've got some definitions we have to get through, some terminology, and then we'll show at the end of class how to make your calculator do it all. Okay? So, this is, let me turn off this front light. This is a scatter plot of some of the shoe size, height data that you had. This was section B for females. Let me flip to your section. And let's see, I think I want to use females because it fits on the board better. So when I raise the screen and I can write on it, then that'll work. If I use the males, then Logan's too tall, so he took this up off of the chalkboard. I guess I have to deal with this string hanging there making a shadow. But you'll see that the x, y axes across there, we have shoe size as our x variable and height as our y variable. And we did this before. Just for some practice, what is the correlation coefficient R? Right? What does that give you? What does that quantify? Okay, she said relationship between two variables. Okay, more specific. You're right, but I want more specific. I want a word added before relationship. Linear relationship. Remember, I gave an example where we had a relationship, but it wasn't linear. The correlation coefficient comes back 0. So you have to specify it. It quantifies the linear relationship between two variables, x variable and a y variable. When you look at shoe size and height, it looks like there is a nice linear relationship between those two. As shoe size gets bigger, so does height. We talked last time about strength of association. What did we call this one? Was this strong or moderate or weak or? Yeah, it's probably moderate, kind of borderline between moderate and strong. I don't remember what this correlation coefficient was for females in section C, but I could page down and find out. Females in section C was 0.657. What did I use as the cutoff? 0.65. So borderline, moderate to strong. So it looks pretty good. You can visualize now fitting a line to that data. All right? So we need to talk about lines and drawing lines. Now, to get into this class, you had to have a prerequisite, and that was college algebra, right? And in college algebra, you learned the equation of a line can be written in several different ways. One way was this. And what's that called? That's the slope-intercept form of the equation of a line. This is y equal mx plus b. The x is the independent variable, or the explanatory variable, and y is the response variable, or the dependent variable. So what is m and what is b? M is the slope, b is the y-intercept. Okay, well now in statistics class, we write it a little bit different. So rather than write it that way, we write y equals a plus bx. we write it differently so that you think you're learning something new. So you feel like you're getting your money's worth out of having a new class. But it's really just the same thing. This is the same form of a line as this. It's the slope-intercept form of a line. Here, B was the intercept. Now, what is B? It's the slope. How do I know it's the slope? Because it's the one that's multiplied by x. So it's the slope. So B is the slope of the line, and A is the intercept, the y-intercept. And that's the form that our calculator will use, and that's the form that the authors of the textbook use. They call it A plus BX. You'll see other textbooks, if you have to go on and take another stats class, they may use different symbols, but it's always going to look like that. Slope-intercept form of a line. Okay? The one I teach my upper level regression class uses B sub 0, B sub 1. So just different notation, but it all means the same thing. All right, well, let's take a look at this data. If I ask you to come up here, take the marker, and draw the line of best fit through those points, could you do it?
Not perfect.
Yeah, not perfectly, but you could get a line that looks pretty reasonable, right? But rather than make one of you do it, I'm going to do it. So I'm going to do, it looks like about there. And I kind of angled off there a little bit. Does that look reasonably good? Again, don't grade me on my artwork. So, let's estimate the equation of that line. Then once we do that, we get a feel for what the line is doing. Then we can use formulas and calculators and computers to actually get it perfect. What's the intercept of this line? And I'll give you a hint. It's not where it crosses right here. Why not?
That's not 0.
That's not 0. This is 5. Right? You can't see the numbers, they're too small. But that's 5, 6, 7, 8, shoe size, right? So if this is 5 to 10, to get to 0, I need to go that distance back this way. So that's about right there. Right? So I need to extend my line until it crosses the true y-axis. So here we go again, don't grade my artwork. About like that. Well, that worked out pretty nice. It looks like it's, this is, you can't read this number either, but that's 50 is where it starts. This is 60, 70. So it looks like it's just a little above 50, maybe 51. Right? So my A is about 51. Now, slope's a little bit harder. How do you estimate slope? Rise over run. So I got to pick 2 points that are on the line and just figure out how much did it go up between those points, how much x change was it. So on the line, it looks like, let's pick this point right there, and we'll pick this point right there because it's on the line. That one looks like it has a height of 70, right? It's even with the 70, and it has a shoe size of 11. So that is the point 1170. This point looks like it has a height of what? 60 is right there. So I'd probably call that 61. So and it has shoe size of 6. So the slope, which we call B, how do you compute that slope?
Y2 minus Y1.
Okay. You take the difference in the y's, that's change in y. So that's 70 minus 61 divided by the change in x, which is 11 minus 6. And that's
1.8.
9 over 5, which is 1.8. Okay, so my B is 1.8. So the equation of my line, I'm going to write like this. Y equal 51 plus 1.8x. And I'm going to put a hat on the Y. Do you know why I put a hat on the Y?
Raining.
Because it's raining today. You know how many semesters I've waited to use that joke? It's the first time it's ever been raining on the day I did this lecture. Now we put a hat on it, seriously, because a hat in statistics means predicted value or estimated value. So anytime in statistics, and this is about the only time in MA 140 you'll see it, anytime you see something with a hat over it, it means this is an estimate of that thing. Right? So Y hat means predicted value. So these are females, so if I want to predict the height of a female with a size 9 shoe, then I can plug that 9 in for X and get back a height, and I have a predicted value. Okay? So let's see. Let me circle this point right there. And that's a girl with a size 10 shoe who is 65 inches tall. So that point is 1065. So the Y value at that point, Y equals 65. Right? What is Y hat at that point? Well, Y hat is the point on the line, right? And it looks like it's at about 67, maybe 68. But wait, I don't have to I don't have to eyeball it. What can I do? Plug it in. Put a 10 in there. 10 times 1.8 is 18. 18 plus 51 is
69.
69. Right? So did the line overestimate or underestimate that girl's height? It overestimated. Right? That prediction error is called a residual.
You only hit one dot on the graph, so there's only one that's not going to have a residual.
Okay, that's fine. I'll come back to that. Hold that thought. Residual is the same thing as prediction error, and that is Y minus Y hat. That's how you compute it. So in this case, that's 65 minus 69, which is negative 4. So here's how to mark that. That distance, it's a vertical distance from the line, is called the residual. So that's my residual, Y minus Y hat, and that's negative 4. Which means that girl is 4 inches shorter than you'd think she would be if you know she has a size 10 shoe. Right? So the negative on the residual tells you it's above the line or it's below the line. The negative says it's below the line, a positive says it's above the line. Okay? Now, Eddie pointed out that, there aren't very many points that actually fall on the line. This one right here is one, and that one that I picked right there is one, and that's about it. Everybody else has a residual, right? It's not unusual at all that a line of best fit doesn't hit any of the points. So what do we mean when we say line of best fit? What does that mean to you? Line of best fit. Okay, it fits the general trend of the data. I like that. But how do you know it's best? The one that I drew does fit the general trend of the data, but it's probably not exactly the best line. What do we mean by best? We have to define it. What does best mean to you, Amy?
Doesn't it mean that equal amounts on each side?
Okay, very good. Equal amounts of points on each side of the line. In other words, it kind of splits through the middle of the cloud of points. Okay? Now, quantify that mathematically. You know, we're becoming mathematicians here. Quantify that. Be precise in terms of residuals.
Oh, if all the negatives and all the positives are added, it should be zero.
Okay? Residuals will add to zero. That's a good point. But that's going to be true even if I tilt the line all out of whack. As long as I go through, I'm going to write this down now. Talk about all regression lines must go through the point x bar, y bar. And what did we call that point? Very good. The centroid. Remember we talked about that a little bit last time? Did I talk about the centroid as being the balance point? Okay. It's kind of hard to do here, but if I look at this, it looks like the mean of the shoe sizes is going to be about a size 9 shoe. So I'm going to mark that point on the line. And that looks like it's about the average of the y points, which vary from here to about there. So that's about the average. So that's my y bar. This is my x bar. All regression lines must go through that point. And it makes intuitive sense. You say, well, I want to split the difference. I want as many above and as many below the line. Well, you need to go through the middle then. And the middle is the central. And it's a balance point in that if I cut this thing out on a piece of cardboard and I put a weight at each of the dots, and then I laid it flat and I put a pencil underneath it to make it balance, that pencil would have to be at x bar, y bar in order to make that thing balance. That's assuming the cardboard has no weight, right? Just where the points are, it would balance exactly at x bar, y bar. You're supposed to be giving me that, wow, look. That's a pretty cool result, right? And it makes sense that the line of best fit, the regression line, should go through that point. So now, back to what Eddie said, if I force it through that point, but I change the slope, I tilt it like a teeter-totter, right? And no matter where I tilt it, as long as it goes through that point, I will have equal amounts of residuals above the line as I do below. And when I sum them, they're going to sum to zero. But intuitively, you think, well, the line of best fit would give you the smallest residuals. And okay, the smallest residuals, I got to quantify that. How about the smallest sum of the residuals? Well, it didn't work because they sum to zero. So what do we do when the negatives are a problem? What do we do when we computed standard deviation? We squared those deviations. We got rid of the negatives by squaring. So we'll do the same thing with residuals. We'll square those residuals. So we'll take y minus y hat and we'll square it. And then what we want to do is we want to get the smallest sum of squared residuals. So we sum the squared residuals and we want to minimize that. Now this is not a calculus course. I wish it were, because then this would be fun. But I did this just the other day for my 346 class, which is regression analysis. We did the calculus to derive the best estimate of A and B, the slope and the intercept. And you use calculus. When you want to minimize a function in calculus, anybody had calculus? You know what you do? What do you do? I don't want to say. You take a derivative, you set the derivative equal to 0, and you solve for the thing you're trying to find. So you can actually do that. And you can solve for a and b and get that. Let me get some room here. What you would derive is that the slope b is r times sy over sx. Huh? What is r? The correlation coefficient. And what's sy? Standard deviation of the y. So in this picture that I now have so cluttered up you can't hardly see the points, in this picture that's height. So that's the standard deviation of the heights divided by the standard deviation of the shoe sizes, the x variable. So you take the ratio of variability in the y direction over variability in the x direction, multiply that by the correlation coefficient, and you get the slope of the line. Now, like I said, it's not a calculus class, so I'm not going to prove that to you. You just have to say, okay, that's the formula. It's been given to me from above. Right? But calculus is above. It's there. It's actually not that difficult. Now, what about the intercept? Well, wait a minute. This is the point-slope form of the equation of a line. But there's other forms, right? There's also the, did I say point-slope? I meant slope-intercept. There's also the point-slope form. Do we know a point this line goes through? It must go through x bar, y bar, right? Which we haven't computed what those are, but we could easily. We could easily compute the average shoe size and the average height of the points on this graph, right? Well, but I don't want to get numbers. I want to do it as a formula. So all I got to do is plug in this point into my equation and solve for A. So when you do that, this is scratch paper. You get y bar equal A plus B x bar, right? I want to solve for A, so I just subtract that from both sides and I'm done. A equals y bar minus B x bar. And I know what you're thinking. You're thinking, I hope this is in my calculator. And it is. Right? It is. We used the calculator last time to compute R. Well, and we did that by pushing the stat button and then Lindrake t-test. Well, as we scrolled down to find R, we went past A and B. So A and B are already computed for us right there in the same screen. Right? And I will not make you compute R by hand. But I might, and so might the online homework, ask you to compute B using this formula. It would be a problem where they say, here's some data, here's a scenario, and here's some data. Here are the summary statistics for X, and here are the summary statistics for Y. And they'll give you X bar and SX, and they'll give you Y bar and SY, and then they'll say, and the correlation between X and Y is, make up some number, 0.87. So once you have those things, you can solve for both A and B. Yeah?
Why would you use the minimize sum of those again?
That's just the method that we use to find a formula for B and A.
Oh, okay.
And I forgot to mention, that's known as the, quote, least squares method. The least squares. I got the squares of the residuals, and I'm trying to minimize that. So the least squares. And there are other ways that regression lines are fit. This was the one that was really first developed back in the late 1800s, early 1900s, sometime like that. But you could think of other ways. Instead of squaring the residuals to get rid of the negatives, we could take the absolute value, right? And then we could minimize the sum of the absolute values. Well, it turns out that that's a tough calculus problem, right? Taking the derivative of an absolute value and then solving, you don't get nice clean answers like this. Another thing you could do is instead of taking the vertical distance as the residual, you could take the perpendicular distance. So the distance from a point to the line perpendicular to that line. The problem with that is every time you tilt the line a little bit differently, then those angles change, and so that distance formula changes. So now you got a really whopper of a calculus problem to try to solve for the slope and the intercept of that line. So this one is most commonly used because it's the easiest to figure out. All right? Remember, this stuff was developed before they had calculators or computers or anything. They had a pencil and they had paper. Right? And an abacus. Right? So you had to compute these things by hand like that. So they want the one that's going to be easiest to compute. But it turns out they have the best mathematical properties as well, which is a good thing. Okay, let me scroll down now. I'll pull this down, and let's see. Nope, not quite. I want to keep my equation on my line that we predicted, or we eyeballed. We had y hat equal 51 plus 1.8x. Right? Now I'm going to scroll down until I have this line actually computed. I got to go past some other slides to get to it. And there it is. Okay. Hey, not bad, eh? See the line I eyeballed in there? Compared to the dotted line. I had it a little bit too steep. And you know, they've done studies that when you give somebody a cloud of points and you ask them to eyeball the best line, the one that they eyeball uses perpendicular residuals, not vertical residuals. And it's always a little too steep. That's just the way it works. But that's okay. So, knowing that my line is a little too steep, the true slope is going to be a little bit less than 1.8. What about the intercept? It's going to be a little bit higher because this end of the line is going to come up just a little bit. Well, right here, in huge letters that I'm sure you can all read, is the equation of best fit. Let me hit slideshow and make it bigger. Now can you read it? The actual line, let me write it over here. The actual line, y hat, is 53.86 if I go to 2 decimal places. And 2 is probably overkill for this. 1.387, so that'd be 1.39x. So there's the actual line of best fit. Here's the one that we did just by eyeballing. And so when you eyeball, you can actually get fairly close. Now, what does that do to our predicted value for our girl that had size 10 shoe and a height of 65? Size 10 shoe, I have y hat equal what? 53.86 plus 1.39 times 10. That's how you get a predicted value at a given x. You just plug that value of x into your regression equation. How much is it?
67.76.
67.76. So it's a little bit closer than what my made-up line had, right? Then we have 69. Oh yeah, it's still over there. So the residual is y minus y hat, 65 minus 67.76, which is negative 2.76. There's the residual for that one. So it overestimated her height by 2 3/4 inches. Okay? All right, remember the mountain bike example? Oh, before I do that, there's one more term. this this discussion is best done with my own drawing, so I'm going to dim this and erase all this stuff. Suppose I have a regression line through those points. Right? So my line of best fit looks like about there. If I take my flashlight and I shine it over here and I project those points onto the y-axis, remember doing this a little bit last time? You're looking at it. Maybe I forgot to do it in your class. So here's a flashlight. I shine, and each of these points makes a shadow on the y-axis. So I get a point here, one here, so on. That spread in those points, ignoring the x variable, that spread is S sub y, right? The standard deviation of the y's. So I'm just going to call that the total variability of y. Okay? And you might say, well, look at this person. Let's say we're still with height and shoe size. Right? Look at this person. That person is the shortest person in the data set. And then I point out to you, yeah, but okay, what was I talking about? This girl's the shortest girl, this girl's the tallest girl, but this one has the smallest x, this one has the biggest x. Right? So some of the variability in the heights between those two girls can be explained by the fact that, well, this one has a lot bigger shoe. Right? So I'm going to do a little magic trick here for you. Right? Nothing up this sleeve, nothing up this sleeve. I'm going to take this line, I'm going to pick it up off the sleeve. And when I do, these points are going to come with it and stay in their relative positions to the line. Right? Now you might have to use your imagination just a little bit with this magic trick. Here we go, ready? Then I move it down and I set it onto the x-axis. So now you see my line? It's sitting there like that, and this point is just right there, this point is, and so on. Now how much variability is there in the y direction? We had this much total variability of y. Now I only have that much. Right? So this is the variability of the residual. Because what I did, I made what's called a residual plot. I plotted the residuals from the line instead of the line itself. Right? Now, the residual variability is the variability that cannot be explained by shoe size alone. For instance, right here, these are two girls with the same size shoe. How come this girl's shorter than that girl? Explain that to me. Trick question. Cannot explain it. I don't know. She didn't eat her green beans. I don't know. Right? Genetics. So there's unexplained variability. Now the fact that this girl's taller or shorter than this girl, I can explain that because her shoe size. She got bigger feet, so she got to be taller. Right? So what I'm doing is I'm taking the total variability and I'm dividing it into explained variability and unexplained variability. The residual variability is the unexplained part. Well, it turns out that the statistic r squared, which is just the square of r, the correlation coefficient, r squared is the proportion of variability in y, which is explained by x, the x variable, or by the linear relationship with x. I just didn't want to write all that. Explained by x. So r squared, when you take your correlation coefficient and you square it, you get a measure of how much variability is explained by the line. So when you do your calculator and you compute r, you'll notice right above it, it says r squared. And you think, well, why do they give me r squared? If they give me r, I can figure out r squared. But they're giving it to you because it's a very common statistic to quote. People say, oh, you fit a linear regression. What was your r squared value? And what they're saying is, how good is your model? How much of the variability did it explain? Now, in this particular drawing, it would explain a lot of the variability. Let me put the one back up here. And over on the right margin, it tells me r squared, rs cubed, and it's 0.43. So what is that number telling me? It's telling me that 43% of the variability in height can be explained by their shoe size. As compared to what? Well, the way the book says it is, another way to think of it is it's the proportional reduction in prediction error. Huh? Well, remember I said a minute ago, what if I asked you to predict the height of the next girl that walks down the hall? What would you use as your predicted value? The mean. Oh, there she is. Hey, what's your shoe size? Thank you. She's gonna the rest of the night. What the hell was that all about? She had a size 8. And her height was 54 inches, or 5'4". How many inches is that? 64, right? 64 inches tall. Okay. Before you knew her shoe size, before you got a look at her, you would have said, well, she's whatever's average. Average, which is about 64. Right? So unfortunately, this is a bad example. I should chew her out for that. But if she had said, well, I have a size 12 shoe, right? Then you might want to adjust your predicted value. Say, well, I'm not going to predict average anymore. I'm going to predict she's taller than average. If she got a size 12 shoe, she's probably taller than average. Right? So how much better can you do by taking into account shoe size when you make your prediction? That's what r squared tells you. R squared is the way the book says it, the proportional reduction in prediction error. So if I hadn't asked her her shoe size, right, then I predict she's at the mean. Now how much better can I do if I take into account her shoe size? Well, that's what r squared tells me. Okay? So I can explain 43% of the variability in height, or I get a 43% reduction in my prediction error when I account for shoe size. Either way you want to say it. Now, how will I put a test question about that? I'll probably have an analysis. I'll have some data for you to fit a line to or whatever. And I'll ask a question like, r squared is this. Interpret that. And you'll have to say, well, it's the proportional reduction in blah, 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 blah. Or I might say, what percent of the variability in height can be explained by the relationship with shoe size? And you have to think, oh, he's asking me what the r squared value is. And you write down what r squared is. Right? So I would ask about it in one of those two ways, probably. Okay, now let's figure out how to do this using our calculator. Now, remember last time we had the mountain bike data? And this was for one of the homework problems at the end of the section. So that data is still in my calculator. So if it's still in yours, great. If it's not still in yours, you need to get it in there, because I want everybody to do this. And you can see the numbers up there. And by the way, this was question 321 on page 113 of the book. And we entered only the front end suspension bikes, the FEs. And there's only one that's missing, so if anybody needs that bottom one, holler, and I'll scroll down and show you what the bottom value is. Is everybody done with the top one? I only have to scroll one off the top. There it is. The bottom one is 140 and 37. So how do I use my calculator to find the equation of the line of best fit? Well, I told you a minute ago, you do it exactly the same way I have you compute the correlation coefficient. So where do we go? Okay, first you push the stat button. Then you go over to test. And then you go down to Linreg t-test. Or you can scroll up and come around the bottom, which is a little quicker, so that's the way I used to go. Press enter when Linreg t-test is highlighted. And then it asks for two things, X list and Y list. Now if you remember, I put my X and my Y's in the opposite list, so you may have done it the other way around. But what you want is the X variable is weight. Weight is explanatory for how much the bike costs. So X should be your X list. I put mine in L2. So just tell it wherever you put your weights. Okay? And then my Y list is L1. That's where I put the prices. What about the next three lines? Freak, B and P, and Reg EQ. Ignore them. We don't care what those are right now. Later in the semester, if we have time, and I don't think I ever do, we'll come back to that. But so just arrow down to calculate. So the only thing you do is you set the X and Y list. So I'll arrow down to calculate. Press enter. And at the top of the output, it says y equal a plus bx. And that's not telling you anything you didn't already know. It's just reminding you of the format of the line. Which one is slope and which one's intercept, right? So then there's four lines that we don't care about. The T, the P, the DF, but the A we care about. So it tells me that A is 2135.50. Since we're talking about money, I'm going to go to 2 decimal places there. And B is not showing, but there's a little down arrow right next to the A. So I go down to B, and that's negative 54.96. So my regression equation is 2135.50 minus 54.96x. Okay? So there's 6 points on the exam. Right? Interpret the number A. What does the number A represent? And she said the y-intercept. And on her exam I would write, that is correct, minus 3. Because I want more than that. And the way I would actually word the question is, what does the number A represent in terms of the problem, in the context of the problem, in terms of weight and what's the other one, price?
The price of a bike that weighs 0 pounds?
Exactly. The price, the predicted price of a bike that weighs 0 pounds. Now, it doesn't always make sense to extrapolate down to 0. You give me a mountain bike that weighs 0 pounds, I'm going to be pretty surprised by that, right? But, you know, theoretically, you could extend the line back, so that's the interpretation. So what it's saying is, if you could get me a bike that weighs 0, you're going to pay $2,135.50 for that bike. Now, I can tell you from experience, that bike's going to cost you a whole lot more than that, right? As you get down and approach 0, the price starts to increase exponentially. It's no longer linear, right? Every ounce costs you another $100 or something, you know. But now, what about B? I will then say in the next part of the question, interpret the number B in the context of the problem. Negative 54.96 what? Well, what is slope again? It's rise over run, so it's a rate of change, right? Our units for our y variable are dollars. So this is $54.96. It's negative. So for every 1 unit change in x, so as a mountain bike increases in weight by 1 pound, what happens to its price? It goes down $54.96. That's what I want as your answer. That's the predicted decrease in cost for every 1 pound increase in weight. It's a rate of change. On the shoe size one, which I erased the real line, but here's the eyeball line we did. This slope, 1.8, what does that represent?
For every shoe size, like it goes up, it's 1.8.
Exactly. What she said, I'll say it loud. For every 1 unit increase in shoe size, so like from a size 8 to a size 9, you'd expect that person to be 1.8 inches taller. Got it? So it's a rate of change. It's the change in y per unit change in x. The intercept is the value of y when the x is 0. Got it? See how easy all this is? All right, that's all the time we have, so I will let you go. And you have homework due tonight over section 3.2, which was the correlation stuff. And this homework over 3.3 will be due Friday night. We have a test coming up a week from today. Get started making out your cheat sheets.
We have a review sheet.
Yes, you will have a review.